All right. So the FDA in their infinite wisdom moved that page, and I'm not sure where the original was or is now. Doesn't matter. All I really wanted you to know is an example. And so I created a new example link to some pH food related material on the FDA's website. And so this one is specifically about acidified and low acid canned goods. And so the link to that, acidified and low acid canned foods, guidance documents, and regulatory information, just to give you one example of how there are regulations, how there are guidelines for producing canned goods or producing food in general related to pH requirements. And there are lots of guidelines, and there's some other things. The document I saw before, kind of liked it just because it didn't just go into canned goods. It talked about the pH of foods in general. So what is the typical pH range for carrots or for corn or for whatever product you're dealing with? I'm sure it's still out there, just was not able to find it in the last few moments. You might notice a background change. I changed rooms as well because the class was about to start. So another reason why pH is important, sanitizers. They might only work in a certain pH range. So when I'm mixing a chemical to clean up after my manufacturing run and I have to clean all the equipment that I used, I have to make sure that the pH is correct for that chemical. Now, a lot of chemistries are designed with built-in pH stabilizers to make sure that they work under a wide range of conditions, but not all of them. And if you've got really bad high acid or low acid water in a bad area with lots of salts and lots of problems, it can throw off sanitizing chemicals pretty badly. So you've got to make sure if you're sanitizing, you're operating within the appropriate pH. Storage containers, certain acid foods might leach out chemicals that can be harmful to people. And so you have to make sure that the container in which you're putting the food, the can, the bottle, the bag, the pouch, the whatever you're using to put something in, that it is appropriate for the pH of the food that's going into that package. So how do you measure pH? pH needs to be monitored regularly in many cases. You need to make sure that you're falling within the guidelines of food safety, of sanitation protocols, whatever your situation is. So you need the right device. Of all the scientific equipment I've seen used over the years, the one I've seen misused the most is arguably pH meters. People using a cheap pH meter that's just not up to the task. It might not be durable enough. Let's say you're doing soil samples. You need one with a really good, solid, durable probe that can handle being poked into soil samples, mud samples, hundreds of times, perhaps hundreds of times a week or even a day. Maybe you're measuring water. One of the hardest things to measure is irrigation water from the well, from drinking water, whatever. There's so little salts in fresh drinkable water that most pH meters have a real hard time with it. So if you're testing the pH of your well water, it better be a pH meter that can handle that. Any pH meter is going to give you a number. It'll spit out a number. Oh, the pH is this. Is that an accurate number? Or is it just confused because it's having difficulty reading your sample? My recommendation, talk to the manufacturer of your pH meter and just tell them, I'm working for a company that does blah, 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 and I'm measuring the pH of water in the irrigation, or I'm measuring pH of tomato pastes or wines, or whatever, and just say, what would you recommend? We're currently using this one. Is this really the best meter for that application? And then talk to a couple other manufacturers. You ask for their technical representative And a good tech rep at a science equipment company will be able to tell you, oh yeah, you're using a perfect meter. Go for it. That I really like that one. Or he might say, I don't know, you could get away with it, but you really should be using this one. That meter you're using is not really up to the task. Or they might say, oh, hell no. Don't you dare use that meter. Stop using it now. It's not appropriate for what you're trying to do. And most people who aren't familiar with it think any meter is a pH meter and they all do the same thing and they all work fine. And you can get the $39.99 cheapy pocket digital thing and it's going to be fine. Not necessarily. So they're meters. These are inexpensive pocket type meters, portable meters. They're test kits. Some of the test kits can be combined with optical sensors. So you're not relying on your eyes to judge color. You can rely on a machine. You do your mixing of your chemicals. You take your little mini test tube, you stick it in the machine, hit a button, and the machine reads the color, taking you out of the equation. So your eyes, the color of the lights overhead don't mess up with the readings. There's also tabletop ones. This is kind of an entry level tabletop science meter, but there are much more expensive ones. Something like this might be 150 to 300 bucks. I had one meter that was more like 10,000 bucks, but it did multiple samples extremely quickly, connected to a computerized system, logged it all in. And I've seen meters for even larger price tags than that were combined with robotic sampling. So you put your samples in and it will automatically take the samples through. You load the machine with your hundreds of samples and walk away. It does the work for you. But pH is just one thing, one number. Doesn't tell the whole story. It only tells you what is the hydrogen ion activity at this moment under these conditions. That's it. And all biological things and most non-biological things have buffers. There's buffers in the clouds, buffers in your lakes and rivers and streams, buffers in your blood, buffers in orange juice, buffers in your morning cereal. Buffers are everywhere. All that buffers are compounds that act as hydrogen ion reservoirs, and they can combine with hydrogen ions, removing them from solution, or they can put hydrogen ions back. They're often called a weak acid-base pair because as the pH conditions change in the environment in that water solution, they can act as an acid, giving up more hydrogen ions to put hydrogen ions back. Or if the conditions change in the other direction, it can act as a base, taking up those hydrogen ions. So it's a weak acid-base pair. Effectively, what it's doing, a buffer resists changes to pH. As you add an acid or add a base, it's not going to change the pH as much as it would without the buffer. It doesn't mean this pH is locked in place, it's rock solid. No, the pH will still move, just not as much. And in some cases, it'll be pretty darn good at holding that pH stable. And we depend on that. Otherwise, your morning coffee could kill you. You drink your morning cup of coffee, it's very acidic, as we earlier learned. If it wasn't for buffers in our blood, what would we do? We wouldn't have the ability to keep our pH of our blood stable where it needs to be, near neutral, and keep us alive. But all biological systems have that, whether it's inside of an orange or inside the leaf of a lettuce, and they're not all the same. Inside an orange, it's going to be acidic. Citrus fruits are acidic. Inside the leaf, maybe it's only slightly acidic. Someplace else, maybe there's even some alkaline or basic. regions within orange tree and all of its organs? Not sure. So buffers are hydrogen ion reservoirs that take up or release hydrogen as needed. So here we have a simple illustration using one of the most simple buffer systems that is everywhere. And it also explains why rainwater, as I mentioned earlier, is slightly acidic. So water in the atmosphere forms clouds, or in a river or lake is churning and it interfaces with the air, the atmosphere. And what does the atmosphere contain? Mostly nitrogen, a bunch of oxygen, and carbon dioxide. There's a small amount of carbon dioxide, and that carbon dioxide dissolves into the water. When that water forms droplets in clouds or it's in the river, carbon dioxide dissolves into the water. So does other gases. Oxygen dissolves in the water. That allows fish to live in the water. They get their oxygen from dissolved oxygen that gets into the water. But the oxygen doesn't react readily with the materials in the water. It can, but we're not going to talk about that. We're going to talk about what happens to that carbon dioxide gas that turns into a dissolved mineral, or dissolved molecule rather, in a water solution, like a drop in a cloud. Water and carbon dioxide can react, forming carbonic acid. And carbonic acid, it's called an acid because these two hydrogens, these two blue circles that represent the hydrogen atoms, are not completely stable, and one of them can be given up. But it doesn't leave with its electron, it just leaves as a proton, a hydrogen ion. So carbonic acid is called an acid because it can react in such a way to give up one of its hydrogen ions, leaving behind bicarbonate, a base. So we've got a weak acid, carbonic acid, and a weak base, bicarbonate. The weak acid is an acid because it can give up a hydrogen ion, making the solution more acid. The weak bicarbonate, the weak base, is called a base because it can combine with the hydrogen ion again, going back to carbonic acid. It can go back and forth. You notice this double-headed arrow. All of this is going on at the same time in a water solution, like a raindrop or a freshwater creek. All of it's going on at once that you see on the screen here. The only thing that's affecting the pH that you see on the screen here is this, the hydrogen ions. So there's an excess of hydrogen ions, not a lot, but a little bit. So fresh water, rainwater and fresh water is slightly acidic. Now there are other things that can go on once it's in a lake or river. It's interacting with the life, it's interacting with the rocks and minerals and soil and everything else around there. So it gets complicated when it's in a lake or river, but even most lakes and rivers are slightly acidic because they are slightly impacted by exactly what you're looking on the screen or what you're seeing on the screen, among other things. This is an oversimplification. There's other things going on, but rainwater is acidic, even not counting acid rain, which is the raindrop is not only dissolving carbonic or carbon dioxide, forming carbonic acid and bicarbonate, it's also all of the human and volcanic things like sulfuric acid and nitric acid. And there's a lot of other things in other concentrations, but don't worry about that. Worry only about this. So what happens when the hydrogen ion concentration is low? What if I add a little bit of base? What does a little bit of base to this rainwater do? It takes away some of those hydrogen ions. So that favors the reaction to make more hydrogen ions. If I add a little bit of base, the carbonic acid makes more bicarbonate and hydrogen ions. What if I add a little bit of acid? I increase the hydrogen ion concentration. I add a little bit of acid. Well, the bicarbonate is going to absorb those excess hydrogen ions I just added and favor the reaction going the other way to make carbonic acid again, to take away the hydrogen ions, again, resisting pH. And so you need to understand not only what is the pH of my vegetable product, my fruit product, my canned good, my recipe, whatever I've got, my food product, but what's the buffering capacity and how will that pH be affected as I do things to it, as it's in storage? You need to understand where is the pH going to move, because pH is not a stable, permanent situation. It will change. If you have a perfectly stable water solution in a bottle, it's going to change, or it's not going to change. It's going to be stable, excuse me. But biological systems aren't that way. Once I'm done canning a product, the biological activity is over. pH is pretty stable for a long time. But there's still things that change, and especially in products that are still alive. The minimally processed value-added foods, we got to know about pH. So how do you adjust pH? What if I need to change the pH? Well, there are food-grade acids and bases available that may be applied in some situations to processed foods and food products that are used to adjust the pH. So you can bring it up or bring it down. In many cases, you're not allowed to do that. It's not legal to adjust the pH. It's considered adulterating the product. You're doing something in an unsafe manner. In some situations, for example, it could be considered that if the pH is already in an unsafe range, you add an acid to bring that pH down, it may be too late. So if you're going to be canning tomatoes, for example, you have to start with tomatoes that are already at an appropriate pH. You can't adjust the pH down of tomatoes that are not acidic enough. That could be considered unsafe. So you just need to make sure your tomatoes, your raw product that you're getting, are sufficiently acid. And most tomatoes are, but not all of them are. I did a lot of work on tomatoes, and I had some varieties of tomatoes that were pH like 4.8. They were yummy tomatoes. They were great for salads and things like that, but they would not be appropriate for canning because the pH is way too high. So in other cases where you can use acids or bases, you can add them if they are already naturally occurring in the product. So tartaric acid, you can add that to wines because it is a naturally occurring material in wines. There's nothing unsafe about using tartaric acid. It is something that is to adjust flavor and wine-making qualities. Citric acid can be used as a stabilizer and a pH adjuster in certain fruit and vegetable products. So there are numerous examples of food-grade acids and bases that are appropriate to use. But you need to know what you're doing. You need to know when I can and when I cannot do it. And that's where you need to do your homework. You need to make sure you are following food manufacturing guidelines and following pH guidelines that are appropriate for any food you happen to be processing.